Okay. All right. Good evening, all. How about the audio? Am I audible properly? And about the video, is it clear? How is it? Audible and clear. Okay, right. Okay, right. Okay, right. So we'll start then. Good evening again. Good evening again. So, how was the week? How did you do? What about studies? And how are the things? Huh? How are the things? How was your week? So last day we finished vectors. Did you practice vectors? How is it now? Huh? All good? Yes, okay. So you are going to have vacation this Friday, right? Yeah, from this Friday onwards, you are going to have a vacation of 1 month. Right. Okay. Right. All right. And another small reminder before starting. So as we planned, now the new batch students are merged to the regular batch this Friday onwards, right? So I saw some of you have already enrolled to the regular batch as well, right? I clearly told you that once you purchase the new batch, right? No need to purchase the regular batch again, it will be free, right? It will be free. So once you purchase the new batch, upload that same payslip that you have purchased the new batch to the regular batch, right? And you can enroll yourself there. And we'll be starting the first class after merging on this Friday. This Friday. Any questions? Please put to the main chat. Studying vacation. Studying vacation. Okay, good. For the regular batch, it says an enrollment key will be yes. For regular batch, the enrollment key is this. For regular batch, this is the enrollment key. PS at capital P simple dash Y 27 TR. This is the enrollment key for regular batch. Right? I thought I shared the enrollment key on the in the last class. No, right? Okay. Then if not, this is the enrollment key for new batch. For regular batch. For regular batch. PS at PHY 27 TR. Right? Hope it's clear. Okay. So any other questions? All good? Okay, 1 second. No, it works. Then probably it might be an uppercase or lowercase something. In your case, it works. Mine worked. Yeah, that's the thing. It works. It works. Make sure that your uppercase and lowercase letters are proper. Okay, right. Okay, what about the ones on YouTube? Give me 2 minutes to check out. Yeah, that's also perfectly working, right? Okay. Okay, it's fine. Okay, it's fine. It's perfectly working. Right. Okay, then let's start. Right. So as we planned today, today we are going to start the fresh lesson in the fresh month, right? That is Newton's laws. So when it comes to Newton's laws is one of the most crucial lessons, critical lessons you are going to have in the lineup of mechanics. The reason is the links we have, right? Newton's laws is going to be linked to most of other places coming up, most of other points coming up in not only in mechanics, in other units as well. So therefore, as a lesson, as a part, Newton's laws plays a major role in our syllabus, right? So now we'll be starting Newton's laws from scratch, right? And most probably my plan is to complete all the theory parts about Newton's laws today itself. So therefore, ending time won't be 10 most probably, right? So it will be around 10:30, 11 or something like that, right? So my plan is to finish all theories by today itself. Then next day we can go ahead with all the questions and finish this off, right? That's a plan. So therefore, now I'll be taking an extension today up to say 10:30, 11, something like that. Let's see with your speed, right? Now if I was able to cover the plan part before that time, then we can wind up, right? If not, my plan is to continue it until 10:30 or 11, right? So I don't think it's a problem, right? So since you are joining online, all of you are joining online, if you need to have some like bottle of water or some snacks, right? You better keep them closer with you. Otherwise, don't try to just go out from the class and come back once the class is started, because you will miss something if you just go out from the class, right? All right, then we'll start. So as the heading, take down Newton's laws. Take down the heading Newton's laws. Newton's laws. Okay, listen. So when it comes to Newton's laws, these are the Newton's laws stated by Newton under motion, right? So other than these three Newton's laws, here we have three laws, right? Other than these three Newton's laws, there are plenty of other laws from the same scientist, from Sir Isaac Newton, coming up in other upcoming parts. In thermal physics, we have laws from Newton, and in viscosity, we have laws from Newton. So likewise, there are more things coming up, right? So these are the three laws Newton stated about or on motion, right? On motion of an object, right? That is what we discuss here as Newton's laws, right? So actually these are called Newton's laws of motion, right? Newton's laws of motion, right? Simply we call Newton's laws. All right. So when it comes to Newton's laws, listen first. When it comes to Newton's laws, there are three laws, right? There are three laws, and actually all three laws are interconnected, right? But we will discuss all these three laws one by one, and then I'll explain the links between these laws, and we will see what actually says by that particular law, right? And when it comes to sums, when it comes to questions, we will be using all three laws as per the requirement in sums, right? So therefore all three laws are very much important, and for some extent I know you have an idea about Newton's laws from O levels, but when it comes to A levels here, some ideas are actually going to be changed, or they are going to be updated rather. So therefore, here onwards, today onwards, right, once you learn about Newton's laws here in A level physics, right, you have to stick to these laws that we are discussing here today, right? Even if you have something in your mind already from O levels, you better forget about it and start from scratch here because in O levels there are some things they are actually hidden, they are omitted when the law is given because of the knowledge and the things you know from O levels, right? But in A levels we are going to the very depth, so therefore the exact 100% correct law is discussed here in A level physics, right? Okay, as a first heading, write down Newton's first law. Newton's first law. Write down Newton's first law. Newton's first law. Okay, first write down the law in red, then I'll explain. First write down the law in red, right? Then I'll come to the explanation. Write down the law. If there is no external unbalanced force, if there is no external unbalanced force, if there is no external unbalanced force acting on an object, if there is no external unbalanced force acting on an object, it is either at rest, it is either at rest, it is either at rest, it is either at rest or moving with a uniform velocity, moving with a uniform velocity along a straight line, moving with a uniform velocity moving with a uniform velocity along a straight line, moving with a uniform velocity along a straight line. Okay, look at the board now. Look at the board now. So even if you know something, as I told you, you better forget it and start hearing to my voice from the beginning. Okay, listen. I'm just checking on the YouTube. Okay, listen. Now, everybody knows F equals ma. Actually, F equals ma is a result of Newton's second law. Listen carefully. Right? F equals ma is actually a conclusion or result of Newton's second law. But yet, same F equals ma can be used to verify Newton's first law. So therefore, I'll be using F equals ma before proving here to verify this. But just know that we will be proving F equals ma in the next law. Right? Look at the board. So everybody knows F equals ma now. We know F equals ma. Right? In F equals ma, F is external unbalanced force. External unbalanced force. Sometimes you might have learned about F in O levels as force. Right? So as I told you, that is not going to work here onwards for A level physics. Now you have to update yourself and upgrade your knowledge. Right? So therefore now update it. That is not just a force, that is called external unbalanced force. Right? And M, that you know, that is mass actually. And A is linear acceleration. Linear acceleration. Right? Power is, we say, acceleration, but that is actually linear acceleration. Right? Now what Newton's first law says is, if there is no external unbalanced force, if there is no external unbalanced force means F should be 0. No force means F should be 0. Right? See what happens. Look at the board. F equals ma. Now if F equals 0, now left hand side of the equation becomes 0. Right? Something like this. Left hand side of the equation becomes 0. But we know m is non-zero for any object. Mass is non-zero for any object. Even if that's a particle, there's a mass. Even if that's a particle, a small particle, there's a mass. There's a non-zero mass. But we know if left hand side of an equation is 0, definitely right hand side should also be 0. Equation එක left hand side එක 0 නම් right hand side එක කොහොමද 0 වෙන්න ඕනේ? LHS equals RHS, right? But we know M is never going to be 0. But we know M is never going to be 0. Therefore, acceleration equals 0. Therefore, acceleration equals 0 from right hand side. What is acceleration? Linear acceleration. Acceleration is rate of change of velocity, right? We have discussed way back in units and dimensions. We have started the discussion about those equations way back in units and dimensions about velocity, acceleration, those definitions, right? So acceleration is the rate of change of velocity, right? So if there is no rate of change of velocity, which means there are only two states possible. There are only two states possible. Either it should be at rest. If an object is at rest, there is no change of velocity. Therefore, no acceleration. And the other possible scenario is if there is no acceleration or if there is no change of velocity, it can be an object which is moving with a constant velocity, a uniform velocity. Those two are the two instances Newton stated about the motion of the object, right? So that is how it can be verified using F equals ma. Got it? So therefore, if acceleration is 0, there are only two possible states, there are only two possible scenarios an object can have, right? Either rest or uniform velocity. Sorry. It will be moving. It will be either at rest. It will be either at rest or moving with a uniform velocity. Or moving with a uniform velocity, right? So this is what Newton stated from his first law, right? So start from here and take it down up to this point. Start from here and take down up to this point. Okay, finish. Finish, right? Next heading, Newton's second law. Newton's second law. Newton's second law. Newton's second law. Okay, again, first write down the law in red. First write down the law in red. Right? First write down the law in red. Then I'll explain the law again. Okay, write down in red. Right? Write down the external unbalanced force. The external unbalanced force. The external unbalanced force acting on an object. The external unbalanced force acting on an object. The external unbalanced force acting on an object is directly proportional to is directly proportional to rate of change of linear momentum. Rate of change of linear momentum is directly proportional to rate of change of linear momentum. And direction of force and direction of force and direction of force is same as and direction of force is same as and direction of force is same as direction of linear momentum and direction of force is same as direction of linear momentum. Okay, tell me what is linear momentum? What is linear momentum? Give me 1 second. So send your answers. Send your answers, please. Okay. What is linear momentum? Tell me as an equation. As an equation, what is linear momentum? Now, we have discussed this equation again back in units and dimensions. What is linear momentum as an equation? Yeah, good. That is mass into velocity, mv, mass into velocity, mv, right? Now, what second law says is the external balance force, which means now in second law, F is non-zero. This is about non-zero F, right? Now in second law, look at the board, now F is non-zero. In second law, F is non-zero. F is non-zero. So what Newton says is that external balance force is directly proportional to, look at the board, directly proportional to rate of change of linear momentum. Look at here again. Look at here again. So we know, see, look at the board. We know linear momentum is mv. Linear momentum is mv. Right? So if linear momentum is mv, what is change of linear momentum? If linear momentum is mv, what is change of linear momentum? How can we write? How can we write change of linear momentum? Simply, yeah, mv minus mu, correct. So I can shrink it and write it as delta mv, right? So we know if we have a difference in velocities, you can write that difference of velocity as delta v. If you have a difference of displacements, you can write it as delta s, right? Delta is the change, difference. So therefore, simply by shrinking this, I can write this as delta mv, no? Isn't it? Delta mv. Delta is change of mv. Now, there is not just change of linear momentum, there is actually rate of change of linear momentum, right? Anything over time is called a rate. Anything over time, anything divided by time is called a rate, right? If there is delta v over d, rate of change of velocity. If delta s over d, rate of change of displacement, right? So likewise, anything over time is a rate. Now, if this is rate of change of linear momentum, it should be delta mv over t. It should be delta mv over t, right? Now I'm going to use that here because it says the external unbalanced force is directly proportional to rate of change of linear momentum. So this is it. So that is proportional to rate of change of linear momentum. Proportional to rate of change of linear momentum, right? So this is what he says. Listen, this is what Newton says from his second law, right? There's no equation yet from Newton's second law. There is only a directly proportional relationship. That's a proportional relationship, right? That's a proportional relationship only. Yet, right? No equation is stated as the law, right? Okay, now using this equation, look at the board. This is how we are going to prove this equation. Look at the board. Look at the board. So as who said it? As yeah, Shagina. As Shagina said, delta mv can be expanded as mv minus mu. No? If V be in final velocity and U be in initial velocity, right? Final linear momentum minus initial linear momentum is change of linear momentum, right? Over T. Now we can take M out. Look at the board. I can take this M out. If M is out, V minus U over T. V minus U over T. Right. Tell me a single term for V minus U over T. What is a single term for V minus U over T? V minus U is change of velocity over time. Yeah, very good. That is linear acceleration. That is acceleration, linear acceleration. Yeah, good. So therefore, we can replace this part as linear acceleration. Now, still that is not F equals ma. That is F proportional to ma. Right? Hereafter, this is the approach. Listen and look at the board. This is the approach. So if we have a proportionate relationship, we know we can use a proportionate constant with an equal sign to make it an equation, right? So in dimensional analysis, can you remember? We had to convert proportionate equations to equations, proportionate relationships to equations using proportionate sign with along with an equal sign, proportionate constant along with an equal sign, right? Same idea, same idea. Now here I'm going to use a proportionate constant as k. Then we can write the same equation as F equals kma. We can write the same equation as F equals kma. But listen, but Newton proves that he proved that as long as mass is substituted in kilograms, always the value of proportionate constant k here is 1, right? As long as k is substituted in kilograms, as long as k is substituted in kilograms, value of k is always 1, right? So with that, he stated the final equation as F equals ma, and as a compulsory rule, right, we have to plug mass in kilograms if we are using F equals ma, right? The only unit you can plug mass here in that equation is kilograms, because k should be 1, right? Therefore, finally, he stated the final equation as F equals ma, right? That is how F equals ma is derived using Newton's second law, right? Law is about this relationship, and after several researchers, now he came up to here, and then again after several researchers, he proved that k equals 1 and set the final equation as F equals ma. That is how F equals ma came into the subject here, physics. That is how F equals ma came into our thing, right? Hope it's clear. Starting from here, take it down. So why is the direction of force part relevant in the law? That's a good question. Listen, that's a good question. Because force, both external unbalanced force and linear momentum are vectors. They are vectors. Whereas mass and time are scalars, right? So therefore, direction of force should be same as direction of linear momentum from the right hand side, because that is a vector equation. That's the reason. That's a good question. Take it down from here. It's clear, right? Right. So therefore, when you are asked to write Newton's second law, the complete law, right? Complete law, as I mentioned just now, you have to write. If only a part is written, no marks will be given. For laws, half marks are not given, right? For laws, half marks are not given. Always full marks are given only for the complete law, right? So therefore, we have to write the complete law without even missing any word. right? Okay, finished. Mention below in a red pen. Mention below in a red pen. Mention below in a red pen. When simple m is substituted, when simple m is substituted, when simple m is substituted, when simple m is substituted in kilograms, when simple m is substituted in kilograms, k equals 1. When simple m is substituted in kilograms, k equals 1. Okay, now write down the equation again, f equals ma. Write down and highlight the equation. Write down f equals ma and highlight the equation. Introduce terms one by one. F, m, and a. Introduce terms f. Right? F is not force. F is not force. F is external unbalanced force. Right? Write down F, external unbalanced force. F, external unbalanced force. External unbalanced force. External unbalanced force. M mass. M mass. A, linear acceleration. A, linear acceleration. A, linear acceleration. A, linear acceleration. Okay. And below that again, mention this point in red. Mention this point in red. F equals ma is a vector equation. Write down below. F equals ma is a vector equation. F equals ma is a vector equation. F equals ma is a vector equation. Therefore, all basic rules regarding vectors. Therefore, all basic rules regarding vectors Therefore, all basic rules regarding vectors are valid. Therefore, all basic rules regarding vectors are valid. Right. Next heading, Newton's third law. Next heading, Newton's third law. Newton's third law. This is the most popular one out of all, right? Most popular law among all, right? Newton's third law, right? What it says is, what is it? Simply, every action has an equal and opposite reaction. Simple as that. Very simple as that. And we can prove that also using F equals ma. We will see how it is going to be proved using F equals ma in the coming parts. Okay, write down the law in red. Write down Newton's third law in red. Every action has a reaction which is which is equal in magnitude, and opposite in direction, Okay, you will see how action and reaction works in the coming parts. So therefore, I'm not going to take a separate time to explain it here again because it is actually coming up in the coming parts. Right. Now, next thing, listen. Next thing. Listen. So next thing is first thing is marking action and reaction forces. Right. The very next thing that we are going to look at is the way that we should mark action and reaction forces. Right. Okay. As the heading take down, marking reaction forces on objects. Marking reaction forces on objects. Right. Marking reaction forces on objects. Okay, write down below. Reaction forces exert. Reaction forces exert. Reaction forces exert. Reaction forces exert. Reaction forces exert due to contact of two objects. Due to contact of two objects. Due to contact of two objects slash two surfaces. Due to contact of two objects slash two surfaces. Due to contact of two objects slash two surfaces. Okay, look at the word. Say we have one object here like this, and I have another random object. This is a random object here like this, right? Listen. So even if two objects are actually in contact, listen. Even if two objects are actually in contact, right? For the ease of identifying forces, which belongs to each other, right? As a standard practice, we keep a small gap between these two objects when we are drawing two objects, right? So we know in reality they are in contact, but since we need to have a segregation between two objects, right? As a standard rule, as a standard practice, we are keeping a small gap between two mutual objects, right? So that is the gap I have kept here, correct? Listen, this is how reactions are marked. Always reactions exert very naturally. They are very natural forces. So therefore, reactions exert as with respect to the direction of contact with an object. Now, as an example, listen. Don't think about anything. Just listen. Say, look at here. Say, this pen is, look at here. This pen is going to be in contact with the palm here, with my palm, like this. Now, because of this contact, listen, because of this contact of the pen, right? Now, my palm is having a moving tendency towards rightward direction, no? Isn't it? Now, when the pen is in contact from this side, see, when the pen is in contact from this side, my palm is getting a rightward moving tendency, right? That is the exact same direction of the reaction force, right? So even if you don't see, now from the palm, this pen is getting an opposite force uh, on the pen itself, right? Now on the palm, with the palm, see, so it is opposite with respect to the palm. With respect to the palm, this force is to the right. With respect to the pen, this force is to the left. Now this is left of me. This is to the left of me. Got it? So that is the exact same direction, and that is how reaction forces are exerting. Now, if someone is in contact from my behind, from my back, right? Reaction on me is towards this side. If someone is in contact from this side, reaction is, my moving tendency is backwards, so reaction is also backwards. So likewise, always when you mark reactions, the exact correct way is think about the direction of moving tendency with respect to that contact. Got it? With respect to the contact. Now, as an example, when this thing in contact from this side, this bottom side here, right? Moving tendency of this one is actually upwards. And when this is with respect to this, when this upper object is in contact from the top side, moving tendency of this one is to downwards. That is the exact same direction reaction forces are exerting, right? And when we are marking reaction forces, this is the rule. Always reaction forces are perpendicular to common interface, common surface, so we call common interface, right? Common surface is the surface which goes through two objects, right? Now in this case, see, look at here. In this case, see, this is called the common surface. This is called the common surface or interface. And always reaction forces exert as it is perpendicular with the common surface, right? Now in these initial force diagrams, listen, in these initial force diagrams, you will be drawing the common surface and then you will be marking the force. But once you master this, once you are familiar with this, actually we don't draw the common surface, and just imagining the common surface, we are going to mark reactions in the coming parts. But now since you are starting marking reactions now itself, right? Now for the initial ones, I recommend you to mark it with the common surface, right? Understood? Now this is how the reaction is marked. Look at here. Now with respect to this one, push on the top one is upwards. So therefore, reaction on this top one is upwards, right? With respect to the top one, moving tendency due to this one on the bottom one is downwards. So therefore, this is perpendicular. Therefore, reaction on the other one is downwards, right? And this pair is called, listen, this pair of reactions is called an action-reaction pair. Now, from this action and reaction, now we can't say which force is action and which one is reaction, right? If this force is action force, this becomes a reaction. And if this force is action force, the other one becomes the reaction, right? That is how they work. So actually they are called mutual action reaction forces. They are called mutual action reaction forces. Mutual means they are on two mutual objects, two objects which are at the same point, two mutual objects. Okay, is it clear? So take it down, and meanwhile if you have any questions you can ask. Take it down. Take it down. Okay, mention this point in red below the diagram. Mention this point in red below the diagram. Mention this point in red below the diagram. Reaction forces are always, mention in red, reaction forces are always, reaction forces are always perpendicular, reaction forces are always perpendicular to the common surface. Reaction forces are always perpendicular to the common surface. And no object is intersected, and no object is intersected, and no object is intersected, and no object is intersected by the common surface, and no object is intersected by the common surface, and no object is intersected by the common surface. no object is intersected by the common surface. Okay. See, now from the common surface, no object is intersected. That is how we identify the common surface, right? So once you draw a common surface, right? If an object is intersected at the contacting point, which means your common surface is wrong. Okay, now we'll see few examples, and I'll let you mark these forces, and we'll discuss one by one, right? Example one. See, now what I need you to do is mark only the reaction forces. I don't need you to mark weights and all other forces, right? Just mark action reaction forces. Action reaction forces are the forces due to contact. Those are the forces due to contact, which means if there is a contact, there's a reaction. If there is no contact, there's no reaction, right? Okay, first one. These are examples. See, examples. First one. This is an object which is kept on a floor, right? So as I told you, a small gap is kept for the ease of identifying forces. Try them out. Try them out. Try them out. I'll be giving you few scenarios. Try them out. Okay. Now this is a wooden block kept on a horizontal floor. This is a wooden block, right? Kept on an inclined floor. Kept on an inclined floor. This is a cylinder. This is a cylinder, and a rod is kept. A rod is kept in contact with cylinder like this, right? Right? Now, if this is a cylinder, see, this is a cylinder. This rod is kept in contact with the cylinder like this. This is a rod and a cylinder, and this is a block with a cylinder, a block with a cylinder. This is a ladder. This is a ladder kept between two vertical and horizontal walls, right? So like this, we can keep a ladder between two vertical and horizontal walls, no? Something like that. A ladder. This is a rod. This is a rod. This is a rod. See, this is a rod. This is a ladder. This is also a rod. This is also a rod. And this is a hemispherical container. This is a hemispherical container. Hemispherical container. Hemispherical container. Okay. Try it out. Try it out. I'll give you 2 minutes. Try out. So ask your questions if there's anything. Right, if you are on YouTube, put it to the YouTube live chat so I can see. If you need me to check your answers, I can check it. If you can put it as an image, as a photo to the chat. Right. Okay. Let's see. Have you finished? Shall we see? Have you finished? Oh, still trying. Now you have to adhere to the rules we discussed, the conditions we discussed when marking action reaction forces, right? And wherever there's a contact, there's a reaction, right? And when you mark reactions, since you are learning for the first time, mark the common surface first and then mark the reaction. Okay, it seems you are still trying. I didn't get even a single reaction on the Zoom, right? So I assume that you are still trying and you are busy with it. Is that done? Okay, good. Let's see then. See, for first one, right? These are contacting surface. These are contacting surface, right? These are contacting surface. Now, if I mark the common surface, see, this is a common surface which goes in between, right? Now, with respect to flow, listen, with respect to flow, right? Direction of moving tendency on this one is upwards because flow is pushing this object from the bottom. Flow is pushing the object from the bottom. So motion is upwards. That is the same direction of reaction upwards or that is perpendicular. Right? And exactly equal and opposite reaction comes on the other visual object. That is what Newton said in his third law. Exactly, equal and opposite reaction comes on the other visual object. Therefore, on the flow, same mark comes. Same mark comes to the opposite direction. Same mark comes to the opposite direction. Is it clear? First one. So if you have anything to be changed, right, please make those changes and correct your answers if there's anything. Second one, see, common surface is here. Can you see? Common surface is here. Reaction should be perpendicular to the common surface. Or perpendicular to the common surface. An equal and opposite reaction acts on the other object like this. Done? Next one. Tell me how many contacting surfaces, how many contacting points, tell me, are here in the third one. How many contacting points are in the third one? Shagina, 2. Others? 2. Tashvi, 1. Anyone with any different answers? First tell me whether it's clear to you about the equilibrium, about the setup there, something like this. Now assume this has a cylinder. Which one? This one. Assume this has a cylinder. Now this is a cylinder, right? Cylinder. And this is kept on a surface like this. See, now this is kept on a surface like this. The cylinder is kept on a surface like this. And another rod is taken, and this rod is kept in contact with the cylinder like this. Can you see? This is kept on the surface, and another rod is taken and kept on the cylinder like this. Now tell me how many contacting surfaces? How many contacting surfaces? Tashi, now Tashi has changed her answer to 2. Any other different answers? 0, 1, 2, 3, 4, 5. What do you say? Still 2. All of you are saying 2. Nope. It's 3. It's 3. It's 3. It is in contact with the flow at this point. And rod is in contact with the flow. Rod is in contact with the cylinder at this point. And rod is in contact with the flow at this point. 3 contacting surfaces. Right? So this is the first contacting surface. Right? And this reaction, so we know if a normal is drawn to a circle, it goes to where? Center. If a normal is drawn to a circle, it goes to center. So if there's a geometry, you should show that geometry, right? So here, therefore, this reaction goes through center. Say R1, an equal and opposite reaction is on the flow R1. And here, there is another contact with this common surface. See, there is another contact with this common surface, isn't it? Right? So this reaction is also going through the center if it is extended. Say R2, if values are different, going through the center. If values are different, don't use same notations, use different notations. And third contact is here at this point. So this reaction is R3 perpendicular to this, and this reaction is R3 perpendicular to this. 3 reactions because 3 contacting surfaces. Is it clear now? Is it clear now? Right? So ask if any questions. All of you said 2. All of you said 2. 3 contacting points. Right. So once on YouTube also, if there's anyone you need to know, please put that onto the live chat so I can see. Oh, R3 is in touch with cylinder. R3 is not in touch with cylinder. R3 is the contact between rod and the flow. Rod and the flow. Right? One end of the rod is on ground, no? One end of the rod is on ground. Otherwise, it cannot be kept at equilibrium. Right? So one end is in contact with the ground. Okay, what about the next one? How many contacting points here? Fourth one. How many contacting points in fourth one? Tell me, how many contacting points in fourth one? 2. 2. Think about the practical scenario here. Think about the practical scenario here. Right? This is a block that is kept on an inclined plane, and this is a cylinder again. It's a cylinder that is kept on the inclined plane, and if a cylinder is kept on an inclined plane, think of what happens and think of the practicability. Right? Use your common sense. Right? That is very important when you are studying physics. Use your common sense, use your general sense. Yeah, there are 3 contacting points. Yeah, it will roll. That's the thing. Since it rolls, now it is definitely in contact with the box. That is definitely in contact with the box. Right? Okay. Then one contacting surface is here. So one reaction here, let's say R1. 1 second. Okay. Then R1 equal and opposite. And we have another contact here, say R2 and R2. And we have another contact here, say R3 and R3. Clear enough, right? Next one, 5. A ladder kept at equilibrium between one vertical and one horizontal wall. Think about the practicability. Ladder එකක් practically තියන්න පුළුවන් විදිය ගැන හිතන්න ඕනේ. Right? So you should be able to think about the practicability. Where the ladder can be kept, or how the ladder can be kept. How many contacting points? How many contacting points? Yeah, 2 there. 2. That is 2. One is here. One common surface is here. So reaction is perpendicular. Say R1. And on the wall, R1. And the other reaction, other contact is here. So this reaction is, let's say, R2. Right? R2. Right. Here, a rod is put into a hemispherical container. A rod is put into a hemispherical container. Let's say a ball, a hemispherical ball, you know balls, right? A hemispherical ball. So inside that ball, a rod is kept like this. Okay, tell me how many contacting points in 6? Wait, I got a question. But did you delete it? I just saw that a question is coming and now it's gone. Okay, how many? It's there. So could it be 4 ladder because it has 2 legs? That's a good question. Listen. That's a good question. Resultant of both legs are considered here for the reaction. Right? Resultant of both of them. That's the reason. Right? That's the reason. Now let's say you have a chair, then chair is in contact with 4 legs. Right? But we don't mark 4 reactions. We'll mark the resultant of all 4 as one single reaction. Right? For our ease. That's why. Yeah, you haven't deleted it. There has been like 2, 3 other messages came into the chat box, so I didn't see it has gone up. That's why. Okay. How many contacting points here? 2. Yeah, correct. 2. So let's assume the center of this hemisphere is here, right? So common surface at this point is this. This is the common surface. Reaction is perpendicular to this common surface. It goes through center R1, and this reaction is R1, and common surface here is this one. This one. Let me extend this a little bit further. Right now, this reaction is here perpendicular to this one, say R2, and this one R2. These are the reactions. Is it clear? Is it clear enough? What about marking action reaction forces? These reactions are also called perpendicular reactions, right? Listen, these reactions are also called perpendicular reactions or normal reactions. Normal means perpendicular, no? Right? So these reactions are also called perpendicular reactions or normal reactions. You will see those words in the coming questions, right? Okay. Any questions from this part? Quickly. Sarah, okay, good. Others? Okay. Clear. Okay. Right, good. Let's move on. As the next heading, write down tensions on strings. Write down tensions on strings. Tensions on strings. Tensions on strings. Okay. Okay. Look at here. Look at here. See, now this is a string. See, this is a string. This is a string. This is a string, no? Do I have a better one? Ah, yeah, I have a better one. See? Uh, see? Now, say this is a string. This is a string. This is a string. Right? Now, if this string is not tightened, if I keep the string like this, what can we say about the tension on the string? What can we say about the tension on the string? 0 or non-zero? If it is not tightened, it is actually 0. It is 0. If the string is stretched, see, if the string is stretched, then we have a non-zero tension. If the string is stretched like this, if the string is stretched, right? If there is released, no tension. If the string is stretched, there is a tension. So therefore, tension force is a force which exerts due to a stretch of a string. Tension exerts due to a stretch of a string. Write down. Write down. Tension on a string exerts. Tension on a string exerts. Tension on a string. Tension on a string exerts. 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 Tension on a string exerts due to stretch of a string. Tension on a string exerts due to tension on a string exerts due to a stretch of a string. Due to stretch of a string. Okay, next point. Next point. Listen. 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 When it comes to strings, we have uh, few types. Few types. Listen. When it comes to strings. So first we have light strings. Light. Light means weightless. Weightless. Right? And then we have weighted strings. Weighted strings. And other than that, we have inelastic and elastic strings. Other than that, we have inelastic and elastic strings. Right. So you can understand light and weighted, right? Weightless and weighted, which means if there is a light string, mass of that particular string is negligible. So we will consider it as 0 for calculations. Right? Very small strings, tiny strings. Right? So weighted means mass is considerable. Inelastic means if a string is not stretchable, not elastic. Elastic means stretching, extending. That is the meaning of elastic. Right? If a string is not elastic, they are called inelastic strings. If a string is elastic means it changes length. Elastic. Right? They are called elastic strings. Right? So we are dealing here with weightless inelastic strings. We are dealing here with weightless inelastic strings. And in the coming parts, we have weighted inelastic strings. Right? Under mechanics, we are dealing with elastic strings. We have a separate lesson called elasticity. So in elasticity, we are dealing with elastic strings. So therefore, for mechanics, we don't have this. For mechanics part, we don't have this, but we will have light inelastic strings and weighted inelastic strings. And first we will be starting our discussion on light inelastic strings. Okay, listen. The first thing you should know is if a string is light and inelastic, tension at any point of the string is same. It is constant. Right? If a string is light and inelastic, tension at any point on the string is same. Right? That is actually happens with f equals ma when m becomes 0. Right? You will see in the coming parts. Just first now understand what I say. That's it. Right? And when it comes to weighted inelastic string, their tension changes from point to point when their mass changes. Right? So with the mass, their tension changes from point to point. That's the basic difference. That's the main difference between these two types of strings. Right. Write down first point in red. Write down. If a string is weightless, write down in red. If a string is weightless, if a string is weightless, if a string is weightless, if a string is weightless and inelastic, if a string is weightless and inelastic, tension of string at any point, so keep these things in mind because these are the logics arguments we will be using to solve sums in the coming parts. So keep them in mind, right? Especially the points that I am mentioning in red. Right. So what did I say? If a string is weightless and inelastic, tension of a string at any point is constant. Tension of any point of string is constant. Next point. If a string is weighted and inelastic. If a string is weighted and inelastic, tension of string changes from point to point. Changes from point to point. Next point, use a normal color now. Use a normal color now. Normal color. Weightless inelastic strings are called weightless inelastic. Weightless inelastic strings are called weightless inelastic strings are called ideal strings. Ideal strings. Ideal. Weightless inelastic strings are called ideal strings. Weightless inelastic strings are called ideal strings. Okay. See. Look at the board. Look at the board. This is a very important part here you need to understand. So stop all your work and look at the board. Stop all the work and look at the board. Very important. Very important. So this is where I'm going to discuss about the way that we mark tensions and the belonging of the tension. Look at here. Don't write anything. Just look at the board. Say here we have two objects which are kept on a surface like this. Say these two objects are A and B. A and B. And another force is applied here and the system is dragged to the right. The system is dragged to the right. So first, check and tell me whether this string is getting stretched or getting released with this force. Think naturally, think practically. Is it getting stretched or getting released with this applied force? What's happening? It's getting stretched because now these are string connected. Then if we are dragging this like this, the string in between getting stretched. So therefore, there will be a tension exerts. Right. There will be a tension exerts. Look at here. Now, if I think of the string, now here I'm drawing the string again. See, if I think of the string, since the string is stretched, look at here. Since the string is stretched, right? If there is stretching, there will be forces which are acting opposite to each other. Then only an object can be stretched, right? Because listen, look at the board. When we look at here on the board, look at here, right? If these forces are towards each other like this, what happens is this is getting compressed. What happens here is this is getting compressed. But if forces are applied away from each other, this is getting stretched. That is clear now? So therefore, if a string is stretched, forces should be acting away from each other. Therefore, tensions on the string should be acting as they are acting away from each other like this. They should act as they are acting away from each other like this. First, tell me whether it's clear. How did I mark the tension on the string here? Correct. Okay, clear. All right. Then, according to Newton's third law, listen. According to Newton's third law, there should be equal and opposite action for any reaction. Tension is also a reaction. That is also an action, right? That is also an action or a reaction, right? So therefore, according to Newton's third law, the equal and opposite reaction of this tension, should be on the mutual object. Now, for this end, at this end, look at here, focus on this end. At this end, the mutual object is A. At this end, mutual object is A. For this end, mutual object for the string is B. Right? Mutual means two objects which are in contact with each other. That's called a mutual object. Two mutual objects. Right? So therefore, at this point, A and string are mutual. At this point, B and string are mutual. Which means the equal and opposite reaction of this tension should be at the same point to the opposite direction on the mutual object. Now, mutual object is A now. So therefore, this is how we mark the tension on A at the same point. That is exactly at here. But for the ease of marking, we are marking it a little bit with a small gap. right? Otherwise, exactly that is here, exactly here, that is exactly here, right? That is exactly here, but usually when we are marking with a small space like this, T, and here also we have another T, right? Now, listen, right? If I mark both action and reaction tensions on the same string, since it is getting confused, that is why I use the string here again. I draw the string here again separately. That's the reason, right? Now tell me, look at the board and tell me to whom this T belongs to. Is it to string or A? This T. To whom this T belongs to? A. Very good. Very good. It's clear now? This T belongs to B. These tensions belongs to a string, right? Therefore, see, see, what we call this is tension on A, tension on A by string, and this is actually tension on B by string, right? And this one here is tension on a string. Tension on a string. By whom? By B. And this thing, tension on string, tension on string by A. That's clear now? I'm going to identify action reaction forces. Action reaction forces are always between two mutual objects. Mutual, right? They are like A and B and B and A, right? X and Y and Y and X. Likewise. Got it? Box and cylinder and box. Those are the action reaction forces. So therefore, can we say, listen. Can we say these two? Can I introduce these two as an action reaction pair? Can I introduce these two forces as an action reaction pair? These two. Can I say these two as an action reaction pair? These two on the string. What do you say? Is it an action reaction pair? These two on the string. Yes or no? Binary answers. Yes or no? Can we say these two an action reaction pair? Yes. What else? Other answers? No. What about the ones on YouTube? Tell me, what do you say? Yes, no, what else? Only binaries. Tell me. Yes or no? Oh, I'll give you a third option. No idea. No idea. So what's tension reaction pair? Could you repeat, please? For any kind of a reaction, right? For any type of a reaction, there is an action. Or in other words, for any type of an action force, there is a reaction, right? So tension is also a type of an action force that is due to stretch, right? That action force is due to stretch. Newton's third law is not only about perpendicular reactions, that is valid for any type of reaction. Tension is a special type of a reaction due to stretch. That is a special type of a force, type of a reaction due to stretch. No. Okay. Actually, it's no. It's no, because this is the tension on string by A. Right? Now, two parties involved at this point is string and A. Then mutual force should also be between string and A. So therefore, mutual force of this one is here. So these two are actually mutual. These two are mutual. And these two are mutual. Right? These two are mutual. Therefore, 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 see these two follows. These two follows what? Follows Newton's third law. These two follows Newton's third law. Right? See, this is the tension on string by A, and this is the tension on A by string. That is the mutual property. That is a mutual property. There no. That is a mutual property. This is the tension on string by A. This is the tension on A by string, mutual. This is the tension on string by B. This is the tension on B by string, mutual. Right? These two are not mutual forces, even though they are equal and opposite. They are not mutual forces. Right? Tell me whether it's clear. These are very important point that you need to understand here before moving on. So, sir, is tension a perpendicular force? As a, no. Perpendicular forces are due to contact. They are due to contact. Tension is always on the string. Tension is on the string. That is something on the string. That is a force on the string. Mutual, yeah, it's mutual. Right? Perpendicular force, if that's a perpendicular force, it should be due to contact. Okay, any other questions? Or tell me whether it's clear. And are the mutual forces equal? Mutual forces. Mutual means equal and opposite. Equal and opposite. Mutual means they follows Newton's third law. So these two follows this pair. This pair follows Newton's third law, and this pair follows Newton's third law separately. Right? Now, when we are marking on force diagrams, listen. Again, a very important thing. When we are marking tensions on force diagrams, listen. When you are marking tensions on force diagrams, usually we mark tensions on objects only, because tensions on strings are not marked because we are dealing with light strings in most of the cases. Therefore, tensions on strings are not marked because we can't apply F equals ma if there's no mass. They are light, no? That's why. Right? So usually we don't mark these two. These are the tensions on a string. These are the tensions on objects. We only mark tensions on objects. But in a special requirement, if we have a special requirement only, we will mark tensions on strings as well. Right? Now this pair is called, right? So I'll be mentioning everything here on the single diagram. This pair is called tensions on what? This is called tensions on objects. And here, this pair on the other side, both of them are called tensions on both of them. They are called tensions on strings. Right. So that's everything I need to explain about this scenario, and this is one of the most critical points you need to understand better. The reason is in most of the questions we are dealing in the coming up parts, the strings will be involved, right? When strings are there, we should know these things exactly when you are marking tensions. Okay, so quickly ask if you have any questions. If not, you can take this down. Will you explain this diagram again? Yeah, I'll explain again. First, take this down. If you are using different colors, use different colors. Right? Then I'll explain again before moving on. Right? And very clearly mark everything. Mark everything in a very clear manner. Mark everything in a clear manner. Sorry. Finished? Oh, I still taking down. Make it very clear to you. Make it very clear to you. Use colors and make it clear to you. And listen, another small message that I wanted to give you at the beginning and I forgot. Sometimes you might have seen the flyers already that I have been sharing a week or 1.5 weeks back. We are starting a special program called Bounce Back Mechanics. Bounce Back for Mechanics for the ones who have missed mechanics from the beginning, right? For the ones who have missed mechanics from the beginning, right? And that program is starting tomorrow at 7 p.m. Right? Sometimes you might have seen the flyers already. My message is, if there's anyone who need to join that mechanics program, right? That is actually something like this. That is a complete mechanics program from scratch, from zero, to cover entire mechanics. And that program is designed for 4 months. 4 months means that is actually for 16 days. That program is designed for 16 days. It covers all theories with questions, from the beginning of mechanics, right? So if there's anyone who is in need about who is in need of that program, you can share the message, you can pass the message among them all and ask them to join. Since we are starting tomorrow, tomorrow will be a free starting day, right? Tomorrow will be a free starting day. That's the first day of the program, and it'll be on Wednesdays at 7 p.m. As a 4-hour class, 7 to 11, right? So if there's anyone in 27 and 26 batches, especially in 26 batch, if there's anyone who has missed mechanics, so that's a chance, that's another opportunity they have to go around another round around mechanics, right? So if there's anyone, your friends, colleagues, relatives, anyone, you can pass a message, you can share my flyers from the channel. Okay, bounce back mechanics. So that will be the only program I'll be conducting as a bounce back program for mechanics, right? Again, after another 2-3 months again I'm not going to conduct another program as bounce back, right? That is only one bounce back, right? And from that one bounce back program I'll be covering everything from scratch. So if you have missed, you can grab it from there, right? That is open for both 27 and 26 students, for both 27 and 26. Okay, so what about this? Finished? Have you finished taking down? Okay, listen again, I'll explain this again quickly. Now, when the string is stretched, right? If a string is stretched, we know there should be forces acting away from each other. If the string is stretched, forces should be acting away from each other, acting away from each other. Then only it can be stretched. So therefore, forces on string, the tensions on the string are away from each other, like this. They are acting as repulsive forces, away from each other, repulsive, away from each other, right? And according to Newton's third law, the equal and opposite reaction on that force, on those forces, should be on the mutual object. So therefore, at this point, mutual object is A. Exact equal and opposite tension is acting opposite to this reaction, is acting at this point on the object. Object here is A, so that is on A. So that is why I labeled as tension on A by string, right? Tension on A by string, because this tension was exerted on B by the string, right? Similarly, now this is the tension at the right end of the string, and equal and opposite reaction, equal and opposite tension should be on the other mutual object here, right? So on B, the opposite tension acts, that is the tension on B by string, right? So since these two are having mutual objects, right? On A by string and on string by A, they are mutual forces. Mutual forces. Mutual forces are the action-reaction pairs. Action-reaction pairs. They follow Newton's third law, right? So similarly, these two are also action and reaction pair, right? But these horizontal pairs are not action and reaction pairs. They are not action and reaction pairs, right? So both of them are called tension on objects. These two are called tensions on strings, right? So from here, the learning outcome is the way that we mark tensions and the belonging, the ownership of the tension, right? Tell me whether it's clear now before moving on. Or if you have any questions, quickly ask. Clear? Okay. All right. Okay. Write down in red. Write down in red. First point. Write down in red. First point below the diagram. Write down in red. Usually, tensions on objects. Usually, tensions on objects will only be marked. Usually, tensions on objects will only be marked in force diagrams. In force diagrams. In force diagrams. Second point. But tension on string acts at the same point. But tension on string acts at the same point. But tension on string acts at the same point. In opposite direction. Acts at the same point in opposite direction. Okay. Listen, look at here. Listen. So that's the exact concept behind this. That's the exact concept behind this, right? And I will give you another small trick when marking tensions. Listen, a small trick. We are not going to write this. Just uh, keep this in mind. A small trick, a hint, and a trick when you are marking strings, marking tensions on strings. If you have marked a tension properly, listen. If you have marked a tension properly, right? The open side of the arrow, like this. The open side of the arrow, this side, open side. The open side of the arrow, right, is the object that tension belongs to, right? The open side of the arrow, you have the object that tension belongs to. See, now open side of this arrow is here. So this tension belongs to A. Open side of this arrow is to here. That tension belongs to B. Open side of this arrow is here. That tension belongs to string. Open side of this arrow is to here. That tension belongs to string. So likewise, that's a small trick that you can use uh, if you have marked tensions properly. The ownership of that tension is through the object which is at the open side of the arrow. Is it clear? Clear enough, right? Okay, then write down. This is something we know, we are just recalling. Weight equals, write down below. Weight equals mass into gravitational acceleration. Gravitational acceleration. Weight equals mass into gravitational acceleration. So therefore, we can write weight W as mg. Right? Take this down. This is something we already know. Okay. Tell me whether mass is a vector or a scalar. Mass. Whether mass is a vector or a scalar. Mass. Is it a vector or a scalar? Mass is a scalar. Mass is a scalar. No direction. What about weight? Vector or a scalar? Weight. Weight. Weight is a vector. Weight is a vector. Direction of weight is vertically downwards. Direction of gravitational acceleration. Direction of weight is direction of gravitational acceleration. Right? Scalar and a vector. Good. All right. So mention below with a red pen. Mention below with a red pen. Mass is a scalar quantity and weight is a vector quantity. Mass is a scalar quantity and weight is a vector quantity. Scalar vector. Yeah. Sharfa. Are you joining today? Sharfa, are you joining today as a newcomer? Okay, in red, write down mass is a scalar and vector is a, yeah, okay, good. Good. Yeah, did you text me on WhatsApp? I actually can't remember the name, that's why I'm asking. Oh, okay, I actually can't notice the name, remember the name. Okay, good, very good. Okay, now let's move on. Let's move on. Okay, question 1. Question 1. Take this down. Take this down. Take this down. Okay, write down the question. Write down the question. Two objects A and B. Write down two objects A and B. Two objects A and B. Two objects A and B. Two objects A and B of masses. Two objects A and B of masses 2 kg and 8 kg respectively. Of masses 2 kg and 8 kg respectively are attached using a light inextensible string. Are attached using a light inelastic strings are also called inextensible strings. Same meaning. Inelastic are also called inextensible. Right? Are attached using a light inextensible string. And a force of 100. A force of 100 newtons and a force of 100 newtons is applied on capital B as shown. Okay, number 1, question number 1. Question number 1. Acceleration of objects. Question number 1. Acceleration of objects. Number 2. Tension on the string. Tension on the string. Okay, that's it. Since this is the first one, I'll explain since this is the first one. Look at here. So if we are using F equals ma, right? The first thing is we have to mark all forces. You have to mark the forces in the respective directions that you are going to apply F equals ma. And if there are perpendicular forces to the direction that you are going to consider, it is not a must to mark those forces, because from vectors you very well know that if there are perpendicular forces to consider direction, they are neglected anyway. Therefore, without the perpendicular forces, all other forces acting on the system we should mark. Right. Now tell me, when this 100 newtons is applied, what about this string? Is it stretched or released? The string is stretched. Right? Stretched. So therefore, tensions on objects act like this. Now this is what you learned before. Therefore, tensions on objects act like this. Right? And other than tensions, we know reaction forces are acting on A and B because of these contacts. Because of the contacts with the flow, reaction forces are acting on A and B. And weights of A and B are also acting on A and B. But if I'm not going to use, the equation, use F equals ma, along that direction, it is not a must to mark those forces. But since it is the first question to you to understand it better, I will mark them. But moving forward, you don't need to mark if you have perpendicular forces. See, now due to the contact, here one reaction comes, let's say RA, and equal and opposite reaction of RA is on the flow. Listen. Equal and opposite reaction of RA is on the flow. But I'm not going to mark RA now with this question because we are not using F equals ma for the flow. We are going to use F equals ma for the object. So therefore, from the action and reaction, I have just marked the force which belongs to A only. Got it? And other than that, we have weight. Weight is mg. Weight acts from the center of gravity. Weight is mg. 2 times g, 20 newtons. Right? So here we have another reaction, say RB, and weight acts from here 80 newtons. Those are the all forces. Right? Now, next thing is deciding in the sense deciding direction of acceleration. Right? You have to decide the direction of acceleration. You have to decide the direction of acceleration. Now the force is to the right. So once the rightward force is applied, we know with this drag, the system drags to the rightward direction. The system drags to the rightward direction. Therefore, the acceleration of objects is going to be rightwards. Very simple as that. Think naturally. Because this is a force which is dragging the system. So therefore, acceleration of A is also rightwards. Acceleration on B is also to the rightwards. Okay, is it clear? Clear, right? Then when you apply F equals ma, right, you have to mention the object you are going to apply F equals ma and the direction, and then only you can apply, because F equals ma is a vector equation, right? Above all, F equals ma is a vector equation. Since there is a vector equation, all rules regarding vectors are valid, right? I mentioned before. So this is like this, application is like this. Say for A, usually we apply F equals ma, listen, usually we apply F equals ma along the same direction of acceleration. Usually we apply F equals ma to the same direction of acceleration. Very simple. Right now, A is this. See, this is my object A. This is my object A. Now you should be able to identify the force frame. This is called the force frame. Force frame means the forces belongs to A. Force frame means the forces belongs to A. 20 belongs to A. RA belongs to A. Only this T belongs to A. Only this T belongs to A. Now we are using the equation horizontally. If you are using the equation horizontally, vertical forces are neglected. So therefore only T comes. Only T comes. So here T equals mass is 2 into acceleration 2A, equation 1. Right? Then do the same for B. Do the same for B, rightward direction, F equals ma. To the rightward direction, F equals ma. This is the force frame of B. This is the force frame of B. Now, there are two forces acting on B. 100 is to the same direction I considered, and T is to the opposite direction I considered. Right? So, we know from vectors, same directional vectors are considered as positive vectors, opposite directional vectors are considered as negative vectors. So, therefore, F is not 100, all forces you have to write, that is acting on the same direction, 100 minus T because of opposite direction. Mass is 8A. I will consider this as equation 2. How many unknown variables are here? Students, tell me, how many unknown variables are here? How many unknown variables are here? That I am interested. Only two, acceleration and tension. To solve two unknown variables, we need minimum two simultaneous equations. Now I have already obtained two simultaneous equations, which means now this is solvable. Now this is solvable, right? So hereafter, listen, simplify these two equations as two simultaneous equations and find A and T. Simplify these two as two simultaneous equations and find A and T, right? So I'll let you do this point onwards, right? If you have any questions, please ask. Take this down and simplify until the final answers. Try now. Start now. Raise your questions if anything. Send me your answers. Send me your answers. Okay, finished. Okay, let's see. Okay, we are getting answers. 10 meters, 10 ms minus 2, 10 ms minus 2. Tension on A, on string by A, 20 newtons leftwards, B, 20 newtons rightwards. What else? Okay, so those are some of the answers I have received. What about others? Are you still doing? Or if you have finished this, I can start the discussion. What about others? Are you still doing? Otherwise, we'll start. What about you? Okay, see. Now simply, I can see there's a plus t here and a minus t here. So therefore, simply I'm going to add these two, right? So you can either plug values and simplify as well. I'm going to add 1 plus 2, right? Then left hand side is t plus 100 minus t equals right hand side is 2a plus 8a minus t to plus t cancels. 100 equals 10a. So a equals 10 ms minus 2. A equals 10 ms minus 2. If acceleration is known, plug acceleration in either of these two equations, and find tension, right? I'll be going with 1 because that's a small equation. From 1, t equals 2a, a is 10, a is 10. So which means t equals 20 newtons. These two are the two answers. Acceleration of objects, it's common, no? It's 10, and tension of the string is 20. Even if you use the other equation, still you will get the same t as 20, right? Take it down. Take it down. Okay, finished? Okay, write down this below the question in red. Write down these points below the question in red. First point, apply F equals ma in red. In red. Apply F equals ma. Apply F equals ma along. Apply F equals ma along direction of motion of objects. Apply F equals ma along direction of motion of objects. Apply F equals ma along direction of motion of objects. Okay, so tell me if any questions from this, or is it clear? Tell me. This is the first question I discussed. Tell me, students, any questions, or is it clear? Tell me. Asana, clear. So would acceleration for both objects be same always? No, not always. Not always. In this question, that is same because connected with the same string, and it drags together. It drags together. So there are cases with different accelerations, and they are actually coming up. Those are towards the advanced applications of Newton's laws, F equals ma, right? So today I'll be covering all theories with the basic applications, and next day you are going to the average level and advanced applications, and we are going to finish off, right? So you will see different accelerations on the next day. So I did it in another way, but I got the same answer. What's the other way? Using for system, is it? Yes. So I didn't use the equation for system. The reason is tension was asked, no? Right? So even if I use the equation for system, since tension is needed, again you have to use F equals ma separately, right? That's the reason. Otherwise, if we just need acceleration, using for system is also a fine option, right? So since someone asked, see, this is also a fine option. For system, if needed, we can apply for system at once. For system, right towards F equals ma. Considering the whole system, then all forces are coming, then 100 minus t plus t equals total mass is 8 plus 2 into acceleration, minus t to plus t cancels, 100 equals 10a, a equals 10. So using for system, at once we can get acceleration, but when finding tension, again you have to apply F equals ma separately to get tension. Otherwise, when we use the equation for the system, tension forces get cancelled, right? Get cancelled. So therefore, just know both. We'll also be applying for the system in coming questions, right? So that is why I didn't apply for the system here in this first question, right? So if someone needs, you can take this down as an alternative method. If someone needs, is an alternative method. Alternative method. Alt method. Alt method. Okay. Is it all good? Or any other questions? What else? Is it all good? All clear? Okay. Then let's move on. Let's move on to the next question. Okay. Next one. See. Next question. Question 2. Question 2. Write down two objects A and B. Write down two objects A and B of masses 6 kilograms and 4 kilograms of masses 6 kilograms and 4 kilograms of masses 6 kilograms and 4 kilograms are attached to a string are attached to a string which goes over attached to a string which goes over a smooth pulley which goes over a smooth pulley which goes over a smooth pulley. Determine acceleration of objects. Determine acceleration of objects. Determine acceleration of objects. Determine acceleration of objects. And tension on string. And tension on string. And tension on string. When system is released. When system is released. When system is released. Okay, take this down. Take this down. Take this down. So you know pulleys, right? Tell me if there's anyone who don't know pulleys. Is there anyone who don't know pulleys? What a pulley is? Is there anyone who don't know what a pulley is? Tell me if there's anyone. I will explain. Otherwise, if you know pulleys, that's the same thing that you are using in wells and elsewhere. You know, right? I'll show you a diagram. See. This is what we call a pulley. This is what we. Is it clear from the camera? Is it clear? Yes. Okay. This is what we call a pulley. A string or a rope goes around and pulley is rotatable. It is fixed from this point. It is fixed from this point, right? Fixed from this point, and it is rotatable about that point. So we can use it when we are using strings like this. See, see. So this is a pulley. This is a pulley. Now, likewise, we can attach masses. Let me show you something with an attached mass. See, something like this. masses can be attached with strings, right? That is called a pulley. That is called a pulley. If a pulley is smooth, actually pulley is not going to rotate. If a pulley is rough only, it is rotating. Now, since they are smooth pulleys, pulley is not rotating, but the string slips on the pulley. The string slips on the pulley, right? Okay, listen. We'll start this. So first, mark all forces acting on this. Mark all forces acting on this. Try marking forces before I explain. Try marking these forces before I explain. Okay, see. So these are the forces acting. First, weights. 60 newtons here and 40 newtons here. Now, because of this 40 and 60, the string is getting stretched, right? How many strings are here? Tell me, students. How many strings are here? That is the first thing you need to understand. How many strings are here? How many strings? Only one, because one string goes over this pulley. Only one string. That one string goes over the pulley, right? So under tensions of strings, I discussed that if there is the same string, tension is constant throughout the string. Tension is constant throughout the string. So therefore, now if I mark this tension as T here, right? This tension belongs to 6 kilograms. Equal and opposite, right? The other tension will be here. That belongs to pulley, right? This one is the other tension. This is the other. On the same string, tensions are same. On the same strings, tensions are same. And we are marking all the tensions which belongs to objects. Now, 6 kg is an object, 4 kg is an object, and pulley is also an object. Right? So that is why I mark tensions at this point and that point. Okay, is it clear? Now, check on forces and tell me in which direction 4 kilograms is going to accelerate, in which direction 4 kilograms is going to move. Check these forces and tell me. In which direction 4 kilograms is going to accelerate? Upwards or downwards? Any idea before I explain? Any idea about it before I explain? Down. 4 kilograms down. This is how it is checked. See, this is how it is checked. Now, there is a 60 newtons here. Look at the board. Look at the board. There is a 60 newtons here, which is acting downwards this string. He is acting downwards this string. This 60 newtons tries to, listen, this 60 newtons tries to drag this string downwards. Right? This 60 newtons tries to take this string downwards. Right? And this 40 newtons tries to take this downwards again. But both of them are acting on the same string. Two ends of the same string, right? Since 60 newtons is the greater force, it wins this battle. Got it? Since 60 newtons is a greater force, it wins this battle. Now, this is the same string, drags with 60 and 40 from its either of the ends, right? Now, if needed, you can stretch this. You can stretch this like this and check it out. Here we have 40 newtons. Here we have 60 newtons. May string ekana mehama daladi. That's the same string. So one side you have 60, the other side 40. Now from 60 and 40, 60 wins the battle. Since 60 wins the battle, 60 newtons goes downwards, right? So when this 60 newtons goes downwards, since this is connected with the same string, right, this side automatically comes upwards. That is connected with the same string, right? Is it clear? Yeah, I'll explain again. First, tell me whether it's clear. Anyway, I'll explain again. Can you explain how you mark tensions? Tensions on objects are at the mutual points where the string and object meet each other. This is one point. So open side of the tensions of objects, no, open side is the belonging object, and this is another point. The tension, the string is mutually contacting with the pulley. So therefore, at that point again we have to mark, and this is another point. Tension and pulley are connected, are in contact, and this is the other point. 4 kg and string are in contact, right? Very much similar to the previous question, the way that I marked tensions in previous question, right? Tension on object is always as the open side of the tension is towards the object, no? Same idea. I use the same idea, right? Okay. So about moving directions, I'll explain again. Now this is the same string. Let me show it from this. Now this is a string. Now on this string, this goes over the pulley like this. This goes over the pulley. This side is having a force of 60 newtons, whereas at this side there is a force of 40 newtons, right? So if needed, you can stretch this and see. Now on this side we have 60 newtons. On this side 40, right? 60 and 40, right? Now from this battle 60 wins. So this side goes down. When this side goes down, automatically this side comes upwards. Is it clear? Quickly. All right. Now I'll give you like 2-3 minutes. Apply F equals ma to the direction of acceleration and try to find acceleration and tension. Apply F equals ma to the direction of acceleration. I told you in the previous one, and try to find tension and acceleration. So from F equals ma, there are more types of questions are coming on next day, right? Now today, with the coverage of these basic theories, fundamental theories, to you to give an idea, I am discussing these simple questions. So next day we'll be doing all other advanced questions. Right? There are more types of questions are coming, right? Different directions of motions, inclined planes, right? And more pulleys, right? Maybe 3-4 pulleys and more strings, right? There are more types, weighted strings, different accelerations. So is the one from the middle of the pulley a weighted string? Not given, and actually we don't need it, whether it's weighted or not, because we don't apply an equation there. This is not a moving part. There is a fixed part. So therefore, we are not interested. This is a fixed part like this. This is a fixed part to the pulley like this. So therefore, we are not interested because to apply F equals ma, we have to have a moving object now. That's why. Apply F equals ma for these two objects. Right? Apply F equals ma for the objects. And another small announcement. I'm planning to start a paper class for your batch, 27 batch, most probably in December. Right? In December, we'll start all latest by January. In December, or latest by January. Right? We are planning to start a paper class for 27 batch 2. Probably in December or January. Latest by January. Right? A paper class. So therefore, go through everything that we have covered so far, and after you are merging to the next batch also, now we'll be covering things faster. So therefore, go through everything and prepare yourself, because in the paper class you will be getting questions from the parts we have covered up until the ongoing point, right? So I'm just saying you, dates are not finalized yet, dates, times and anything is not finalized yet. Now I'm planning to start the paper class in December or January. We have plenty of time to write papers also, so don't worry, we have plenty of time to write papers also. So that's why I'm starting the paper class even earlier compared to 26 batch, much earlier, even earlier compared to 26 batch, to you to get familiarized with paper writing from the beginning, from the very beginning, right? The inquiries also came from one of the, not one actually, I think 3 or 4, few of the students from your batch, whether I'm doing paper classes for 27 batch. Yes, I'll be doing, and we are starting. I'm planning to start in December or January, right? So you can get to know details about that through the channels and groups in the coming months, right? Okay, any answers? So what's the application? What's the application? For 6 kg, for 6 kg, moving direction is downwards. So apply F equals ma downwards, right? Forces are 60 minus T equals mass is 6A, equation 1. Then for 4 kg, its moving direction is upwards. So apply F equals ma upwards. Vertically upwards we have T. These are the force frames. These are the force frames which belongs to these objects. These are the force frames, right? Then T minus 40 equals 4A, equation 2. So identify forces. These two tensions belongs to pulley. These two tensions belongs to pulley, not for objects. Weight and this tension belongs to 6 kg. Weight and this tension belongs to 4 kg. Right? So simplify these two and find answers. Okay, let's see. Two ms minus 2 tension 48 plus 3. Second 2 and 48. Good. Second, you were not there in the live class for last 2-3 weeks, right? What happened? You were busy with that work. I saw some videos or something that you have shared. Yeah, you were busy with that thing. Some festival or something, right? Festival. A church function or something. Oh, right. Okay. Right. See? Now again, I'm going to add these two. 1 plus 2. 1 plus 2. 60 minus t plus t minus 40 equals 6a plus 4a minus t to plus t cancels. 60 minus 40, 20. 20 equals 10a, which means a equals 2 ms minus 2. Right? If acceleration is known, use either of these two equations to find tension, I'll be using 2. From equation 2, we know T minus 4D equals 4A. A is 2, so T equals 48 newtons. T equals 48 newtons. Okay. So I saw the correct answers from most of you. Good. So correct it. Correct. Correct it if there's anything to be changed from your side. Write down. Okay. Is it clear? Any questions on this one? Any questions? All clear? Is it all clear? Or any questions? Tell me. Is it all clear or any questions? Clear. Okay, good. Okay. Right, let's move on. Let's move on. Write down the next heading. Next heading. Determination of internal reactions. 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 Okay. Listen now. Listen. Internal reaction means if two objects are contacting each other, right, from their walls, each other, those are called internal reactions. Internal in the sense they are the internal reactions for the system. Internal for the system, right? So I'll explain this using a question itself, an example itself. See, this is an example. See, look at the board. Look at the board. Say we have two objects like this. Say we have two objects like this. Two objects, right? Let's say mass of this one is 10 kilograms. Say A and B. And mass of A is, let's say, 20 kilograms. And the system is pushed. System is pushed with an applied force of 120 newtons. Right? System is pushed with an applied force of 120 newtons. Okay. Tell me, how many contacting points are here in this system? How many contacting points in this system? How many contacting points? 2, 4. What else? 3. What else? Yeah, it's actually 3. It's actually 3. Yeah, it's actually 3. It is 3. It is 3. It is 3. One contact is here. Another contact is here. Between one is A and flow. Second one B and flow. Third one A and B. Right? Now, these reactions due to the internal contact. These reactions due to internal contact are called internal reactions. These reactions due to internal contact are called internally in the sense that is internally in the system. Right? System means both of them now. So that is internal to the system. They are called internal reactions. They are called internal reactions. Now in this case, we are going to determine these internal reactions. Got it? Got it? Now there are ways to determine the other perpendicular reactions as well. Now in this question, we'll be finding both, but main focus is on finding these internal reactions, right? So based on the other contact, I'll be marking all forces like this. Weights is there, no? Weights is there. If it is 20, that is 200 newtons. And from here, a reaction acts. From here, a reaction acts. Let's say RA, reaction on A. And from here, another reaction, let's say RB, reaction on B, and weight 100 newtons. So those are the all forces acting on this system now. See, these are the all forces acting on this system now. Right. So first we are going to find these internal reactions, and then we'll see how to find RA and RB as well in this question. Right. Okay. Now take this down. Take this down. Take this down. And mark all forces properly. Right. Okay. Now look at the board. Look at the board. Look at the board. Now we are going to find these internal reactions. We are going to find the internal reaction. Before finding internal reactions, to find a force, we should know acceleration. To find a force, we should know acceleration. So therefore, first thing, I'm going to determine the acceleration of the system. Tell me, once this force is applied, 120 newtons on the system, once the system is pushed by that 120 newtons, in which direction the system is going to be accelerated? What is the direction? What is the direction? What is the direction of acceleration? Yeah, rightwards. Simple now, common sense. Rightwards. So therefore, I'll be marking that acceleration here as A, like this. Right now, here I'm going to use this for the system. See, we can use for system as well if needed. For system, rightwards, F equals ma. Right? When we are using the system, right, all these forces are coming. Can you see that? Leftward reaction, leftward R here cancels off with rightwards R, no? So therefore, at once I can write only 120 remains. At once we can say only 120 remains. Got it? Only 120 remains because these two are going to cancel, right? For your clarity, I'll be writing, but if you can see it as cancelling, you don't need to write even. M is total mass of the system, 20 plus 10 into acceleration. These two cancels. So 120 equals 30A and A equals 4 ms minus 2. Acceleration of the system is 4 ms minus 2. Right? Now acceleration is known. We can apply F equals ma for either of these two objects, A and B, separately, individually, and find simple R, for find capital R. Got it? Because if I consider the system, R get cancelled, which means you have to consider one object out of these two, one separately, and apply F equals ma again. Since acceleration is known now, you can find R, right? So now acceleration is done, and I'll give you 2 minutes again to find R by using F equals ma to one of these objects separately, right? You can use F equals ma for any preferred object by you in the same direction and find R. Okay, start now. Okay, one says 80 newtons. Others, any answers? Other answers? Or is it same? Tarsana, left 40, right 80. That actually you have to check again. Because the reason is leftward R and rightward R are two mutual reactions. Since they are mutual, they should be equal and opposite. Right? So please check your simplifications again. because they should be equal and opposite. Others? Any other answers or any different answers for 40 and 80? What about you? Or any other different answers? Different answers or same? What about others? Cesara, Sara. Who else? Who else? Who else? Minari, Shafra, Shahina, Shahina David, Tashi. Tashi, you have said 80. Yatarsana, you got 40. What about others? Zara, 80 to left, 40 to right. Now, as I told you before, you won't get two different answers for these two because they are equal and opposite reactions. That is why I have marked them as R and R, equal and opposite. So either way it should be same. Either way it should be same if your application is correct. Okay, let's see. Since this is the first one. See. So there are two methods basically. Method 1. Look at the board. Method 1. Method 1. Right. I'm going to use F equals MA for B. F equals MA for B. Rightwards, horizontally rightwards. Right. So this is the force frame of B. See, this is the force frame of B. This is the force frame of B. Now you should be able to segregate. Listen, you should be able to segregate the forces and the force frames. Right. This is the force frame of B. So only force which acts towards this direction is R. Only force is R. Mass of that is 10. Acceleration is 4. So it says R equals 40 newtons. It says R equals 40. Right? To do the same, if needed, what you can do is you can use F equals MA again for A. To do the same, these two are two alternative options. Right? Or else you can try this method 2. F equals MA for capital A to the right. Capital A to the right. Right? Then this is the force frame of A. See, this is the force frame of A. This is the force frame of A. This is the force frame of A. Forces acting to the rightward direction on A is, we are applying for A, right? On A is 120. And R is acting opposite to my direction, that is minus R equals M. Mass is 20 times acceleration is 4, right? So 120 minus R equals 80. Subject R equals 120 minus 80, R equals 40. So that is what I told you. If your application is proper, if your application is correct, either way you will get the same answer. Right? When you are considering an object, you have to consider all forces along the considered direction. Right? Only force that you can neglect is the perpendicular forces. Only type of force that you can neglect is perpendicular forces. Right? So that's a thing. So I know when you say 80, what the mistake you have done, right? You have mistakenly missed the force 120. That is also acting on A. So you have to consider it, right? That's a mistake. Take it down. and ask if any questions. But sir, is the 120 newtons not acting on both blocks? No, only on A. Only on A. Right? 120 belongs to 120 is in contact with A. So it acts only on A. Right? And indirect impact of 120 is transferred to B as through this reaction. Otherwise, 120 is not belongs to A, not belongs to B. Right? That belongs to A. Right? If the force is not in contact with that particular object, anyway that is not belongs. Anyway, that is not belongs to that particular object. Right? If a force is applied, the force is in contact with that particular surface. Right? So likewise, you have to separate force frames. You have to separate force frames. 120 only belongs to A. And this leftward R belongs to A. Rightward R belongs to B. RA belongs to A. 200 newtons belongs to A. RB belongs to B. 100 belongs to B. Likewise. Okay, finished? Finished? Oh, still doing? Okay. Write down below in red. Write down below with a red pen. With a red pen, write down. All forces acting on an object. All forces acting on an object. All forces. All forces. All forces acting on an object along considered direction. Along considered direction. Along considered direction. Should be considered when applying F equals ma. Should be considered when applying F equals ma. Should be considered when applying F equals ma. Right? Okay, don't write. Don't write. Just listen. Only force that you can neglect when you apply F equals ma is the perpendicular force. Only force that you can neglect is the perpendicular force. Right? That's the idea. That's the idea. Right. Next. Okay. So before that, any questions? Is it clear now? Is it clear about the internal reactions? So these are the internal reactions. 40 newtons on each. So these two follows Newton's third law. They are equal and opposite reactions. Mutual, because this is the reaction on A by B and this is the reaction on B by A. Mutual. It follows Newton's third law. Is it clear? Quickly, tell me before moving on. Is it clear? Okay, next. See, now we are going to find the perpendicular reactions as well. Perpendicular reactions are RA and RB. Perpendicular reactions are RA and RB. Right? Perpendicular reactions, or they are also called normal reactions. We are going to find RA and RB now. Right? To find RA and RB, what my approach is applying F equals MA again along that vertical direction. Along that vertical direction. So before that, tell me, what can you say about the acceleration of objects along the vertical direction? What can you say about acceleration of the objects along vertical direction? Tell me, what is your thought? Is it 4? Is it 4? Or is it different from 4? Gravitational acceleration? No. Gravitational acceleration is only when something falls freely under gravity. This is on a flow. This is on a flow. It doesn't fall down. It doesn't fall. It doesn't do any motion under gravity like this. So it is on the flow. What else? What do you think, others? I'm asking about the acceleration. Vertical accelerations on objects. Vertical acceleration. Now we know horizontal acceleration is 4. Horizontal acceleration is 4. What I'm asking is about vertical acceleration. Is it 4 or different from 4? If that is different, tell me what that value is. Not equal to 4. Then what that value? What's that value? Any thoughts? Any thoughts? Anyone who says it's 0? Anyone who says it's 0? Is there anyone who says it's 0? 0. Yeah, actually it is 0. The reason is, now even though, listen, this is a very important part, again very important. Even though this object moves horizontally it is moving with 4ms minus 2, horizontally moving, but there's no movement vertically. There's no vertical movement. If there's no vertical movement, how come there be a vertical acceleration? Because if there is moving vertically only, there is a vertical acceleration. If the object is not moving vertically, there is no vertical acceleration. That is the logic. That is the argument. Right? No contribution from this acceleration as it is horizontal. That is horizontal. No contribution on the vertical direction from that horizontal acceleration. No movement horizontally. This is moving only along the plane horizontally like this. No movement vertically. No movement vertically. Therefore, no vertical acceleration. If there's no vertical movement, there's no vertical acceleration. Is it clear? Is that idea clear? So always when you think of the acceleration, you have to think of acceleration based on the direction. With the direction, right? Okay, see, now this is what I'm going to do to find those forces. Again, for capital A, what you can do is apply F equals ma vertically upwards. Apply F equals ma vertically upwards. On A, for A, vertically upwards I have RA. Vertically upwards RA. Vertically downwards 200. Right? Mass is 20. But very important, acceleration is 0. Vertical acceleration is 0. Vertical acceleration is 0. This is a vertical acceleration. Because I'm using the equation vertically. Vertical acceleration is 0. Right? Which means 20 into 0 is 0. 0 into anything is 0. Which means RA minus 200 equals 0. RA equals 200 newtons. RA equals 200 newtons. So that is how that reaction becomes equal to the weight of the object. That is how it's happening. Right? That is how it's happening. Reaction is equal to 200 newtons now, RA. Similarly, you can find RB as well. Right? Take it down and find RB. Take it down and find RB. And if you got any questions, please do raise. If any questions, please do raise. right? Then you can do the same for B. For B, upwards, F equals MA, right? Upwards, you have RB. Downwards, 100. Mass is 10, but still acceleration is 0, which means RB equals 100 newtons, right? RB equals 100 newtons. RB equals 100 newtons, right? Is it clear? Now, this is how we find perpendicular reactions, normal reactions. Is it clear? Any questions? Or is it clear? Clear, good. Mention this point in red. Mention this point below in red. Mention this point below in red. Mention this point below in red. There is no acceleration. There is no vertical acceleration. Mention in red. Mention in red. There is no vertical acceleration. There is no vertical acceleration. There is no vertical acceleration on objects as they don't have any vertical movement. 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 Next point, keep using red. Next point, keep using red. Next point, keep using red. There is no contribution from horizontal 4ms minus 2. There is no contribution from. There is no contribution from. There is no contribution from. There is no contribution from horizontal 4ms minus 2. 4ms minus 2 along vertical direction. Along vertical direction. Since it is perpendicular. Since it is a perpendicular direction. Since it is a perpendicular direction. Since it is a perpendicular direction. Right? Okay, listen again. Listen again. If there is no acceleration along a particular direction for an object, we call, listen now, listen. We call as that object is in equilibrium in that particular direction. Equilibrium means balance. Balance, no? Equilibrium can balance. Right? Forces are balanced. That's the idea. If there is no acceleration along a particular direction, forces are balanced. See, that is what is happened. Ra equals 200. Upward force equals downward force because no acceleration. RB equals 100. Upward force equals downward force. That is called an equilibrium. Right? So simply, if there is no acceleration along a particular direction, we call that is an equilibrium. Right? Now here there is only a vertical equilibrium, but horizontally there is not an equilibrium. Right? So equilibrium is actually a next lesson, the upcoming lesson, next lesson coming up. Right? After linear momentum, we have force equilibrium. So therefore, now from here just get the idea. That is why I explained you the word equilibrium. Equilibrium is when there is no acceleration. That is a separate lesson coming up. Okay, mention that point again in red. Mention this again in red. If there is no acceleration, mention in red again. If there is no acceleration, for an object, if there is no acceleration for an object along a particular direction, if there is no acceleration for an object along a, say, certain direction, if there is no acceleration for an object along a certain direction, it is at equilibrium. It is at equilibrium. It is at equilibrium it is at equilibrium. It is at equilibrium along that direction. 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 Okay. Right. Tell me if any questions about this. Now here we discussed two new things. One is the determination of internal reaction, and the other thing is determination of normal reaction. We discussed two new things. Tell me whether it's clear or any questions. Tell me. All clear. Good. All right. Okay, good. Good. Very good. Okay, we'll do another example. We'll do another question. Now, this is the example. Right? This was the example. Now we'll do another question. Okay. See? Go through all these things when you are coming to next class, because in the next class, now today I'm completing all the theories, all the theory parts we are completing today, except weighted strings, right? Two things, except weighted strings and different accelerations. All foundation, all the fundamental theories will be completed today, and therefore next day I'll be starting from the point we are stopping today, and we'll be starting the discussion on questions, the sums, applications from the very beginning of the next day. And next day is going to be a full day of applications of Newton's laws. So therefore, it's a must to go through everything, right? Otherwise, if you can't remember these theory parts when you are coming to next day, right, it is not going to work the anticipated way. So therefore, go through again and again and practice these questions I discussed here again at home, right? You have got 7 whole days. And don't forget to join to the Friday class, right? Regular batch class, right? Because there you will be starting center of gravity, right? So there you will be starting center of gravity, another new lesson. Okay, next question. Next question. Okay. Take this down again. Capital F. And this is M, and this one is 3M. So we have to join this Friday as well. Yeah, this Friday. Starting from this Friday, right? Now I have been telling this from the very beginning of last month, right? What's the date coming? 7th. Yeah, 7th. Right? So you will be merged with the regular batch this Friday onwards. 7th Friday onwards. 7th. Yeah, 7th. Class is at 3:30 p.m. to 6:30 p.m. on Friday, right? So therefore, please enroll to that class before Friday. That is better, no? Otherwise, don't wait until the last moment, right? That's why I gave you the key as well. So if you didn't get the key, drop me a private message, then I'll send the key. Enroll yourself to the regular batch, right? So that is what I explained even at the very beginning of this class, right? Don't purchase both classes. Once you purchase new batch class, this class, right, you can join to the regular batch free. So upload the same payment slip to the regular batch class, and you can still join the regular batch class, right? Okay, write down the question, right? I'll be circulating a message to your class group as well, right? Because even though I have been telling this from weeks now, right? Still, there are some of you that you don't know whether we are going to merge on this Friday or not, right? So therefore, I'll be circulating a message again as a reminder. As a reminder, I'll be circulating. Okay, write down. Two objects of masses m and 3m. Two objects. Two objects of masses. Two objects of masses. Two objects of masses. Simple m and 3m. Two objects of masses m and 3m are pushed using a horizontal force applied on a horizontal force F, a horizontal force capital F, are pushed using a horizontal force applied on simple m as shown. Using a horizontal force applied on simple m as shown. Using a horizontal force applied on simple m as shown. Using a horizontal force applied on simple m as shown. Right? Horizontal force applied on simple m as shown. Determine reaction between determine reaction between m and 3m. 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 Okay, give it a try. Give it a try. I'll give you like 3-4 minutes. Give it a try, starting from scratch. Try it. Send your answers if you got anything, got something. One says, what is the answer? Actually, 3SO, 3FO4. 3FO4. You mean acceleration or the reaction? Reaction. Ah, yeah, it's reaction. It's reaction. Okay, not the acceleration. No, M is given. 3FO4. Okay. Internal reaction. Okay. Others? Arkham. Are you joined just now? Is it? I didn't notice that you were there. Acceleration F4M, reaction 3F44. Okay. Yes. Okay. Shikina. 3F44. Okay. So good, good. You are getting answers. You are getting answers. Good. Okay. So before determining internal reaction, first of all, you will need the acceleration. Right? First of all, you need the acceleration. Right? So therefore, the easiest way is apply F equals ma for whole system. For system, rightwards, F equals ma. For system, rightwards, F equals ma. Right? So only F remains on the system is F, because internal reactions are going to cancel each other. Right? Always one feature that we can observe, that we can notice in a system is, if you consider the whole system, all internal reactions cancel each other. All internal reactions will cancel each other. They are internal, so therefore it cancels each other. Total mass m plus 3m, that is 4m actually. Acceleration. So acceleration is F over 4m. Acceleration is F over 4m. Right. Now if I mark these reactions, this is how internal reaction acts. R and R. This is how internal reaction acts. That is how internal reaction acts. Right. Now I'll give you another trick here. When you have, listen, when you have more than one option to find the same force. Now here we have two options. you can either use the force frame of simple m, or else you can use the force frame of 3m. Always, when you choose the force frame with less number of forces, your simplification will be much easier. Therefore, when you have an alternative, you better choose the force frame with the lesser number of forces. Right? That is the fastest simplification, the shortest and the fastest simplification. Got it? So therefore, even though we have two options, now I'm going to choose 3m because only one force acts on 3m. Right? So I'm going to use 3m, this one. Then for 3m, 3m rightwards, F equals ma. Right? Only force act on 3m is r. Mass is 3m. Acceleration is f4 4m. M to M cancels. Reaction equals 3f over 4. Reaction equals 3f over 4. So I show the correct answer in most of your cases. Very good. I show the correct answer in most of the cases. Good. Good. Right? Acceleration is f over 4m and internal reaction is 3f over 4. All right. Is it clear? Is it clear? Clear, right? Quickly, tell me. Is it clear? All right. Okay. Write down below. Write down below. Write down below. Choose the force frame with in red, in red, in red, in red. Choose the force frame with. Choose the force frame with. Choose the force frame with. Choose the force frame with minimum number of forces. Choose the force frame with minimum number of forces. Choose the force frame with minimum number of forces. For faster simplification. For faster simplification. For faster simplification. So either way, right, one way or the other, you will get the same answer. But number of lines you have to spend will differ. Right? So if needed, you can try out by applying to simple m. Same answer comes, but you have to simplify with a common denominator. Right? You have to get a common denominator, you have to consider a common denominator and simplify. Then see what's the number of lines it takes. Right? Now I'm not going to apply for this one. So you can give it a try and see the difference. You can see the difference between number of lines. Right? That's the point. Okay. Now all theories I plan to discuss are finished by now. Right? But we will discuss one more question from an inclined plane. That is better than we have discussed all the types of all means like most of the types of questions we have to get the first idea. We'll discuss one more question from inclined planes and we'll wind up. That's fine, right? That's okay, right? Otherwise, you thought we were supposed to stop at 10. Yeah, good. Okay, next question. Okay, next question. Next one. Take this down. This is a fixed pulley here. Write down. Okay, write down two objects. Write down two objects of masses. Two objects of masses. Two objects of masses 6 kg and 4 kg. Two objects of masses 6 kg and 4 kg are attached are attached are attached to an ideal string 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 which goes over a smooth pulley which goes over a smooth pulley which goes over a smooth pulley. Determine 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 acceleration acceleration of objects determine acceleration of objects determine acceleration of objects determine acceleration of objects and tension of string and tension of string and tension of string when system is released from rest when system is released from rest when system is released from rest when system is released from rest. When system is released from rest. Okay, take this down. Take this down. Okay, then mark all forces acting on the system. Mark all forces before I mark. Try to mark all forces acting on the system. Okay, look at here. Look at here. First, I'm going to mark weights 40 newtons, and here weight that's vertical downwards 60 newtons, right? Then these are tell me how many strings? How many strings? How many strings are here in this setup? How many strings, students? Yeah, only one. There is only one, which means same tension will be throughout. Same tension is throughout. So T at the pulley, T again, and here T again, and here T again, same T. Right. So mark all forces like this. Now there's a problem. There's a problem. Problem means actually that's a difference from the previous questions we discussed. Right? That is now 6 kg is going to accelerate along the plane. We don't know whether it's upwards or downwards, but that is somehow along the plane. And 4 kg is going to accelerate vertically upwards or downwards. I didn't check about the reactions yet, right? But here I can see there is one inclined force. Now for that particular direction along the plane, 60 newtons is an inclined force. 60 is inclined. Since 60 is inclined, first of all you have to dissolve 60. First of all you have to dissolve 60. So please dissolve 60 now. Dissolve. Mark components. Components mark karanta. Mark components. To mark components, we will need an angle. See how we can find out an angle. See how we can find out an angle. Look at here. I'm going to use some triangles. See, I'm going to use some triangles. Look at the board. This is 30. Now this is a right angle triangle. Since there is a right angle triangle, if this is 30, if this is 90, this angle again has to be 60, no? That is 60. Because we know, right? We know internal angles of a triangle is 180. Sum of internal angles of a triangle is 180. Right now, this is 60. If that is 60, can you see that there's another small triangle created here at the other side? Here, a small one created. Then if this is 60, opposite angle to that angle is also 60. Right? Opposite angle is also 60, which means the angle here at the vertex is going to be 30 again. Which means this angle at the vertex is 30. Right? If you didn't get it, I'll draw these two triangles I used here again as a zoomed view here. See, this is what I used. These two small triangles. Right? These two small triangles. This was 30. This is 90. So this is 60. If there is 60, this angle is also 60. This is also 60. This is also 60. This is 90 now. So therefore, this is going to be 30. So that is why this becomes 30. Is it clear how I determine that angle as 30? Is it clear? Use triangles. There's no trick behind that. Use triangles, especially right angle triangles. So always you better means you have to draw these diagrams in kind of a large enlarged manner. Otherwise, you don't see these angles properly. Tell me, is it clear? Is it clear? Quickly. Yes. Zara, yes. Others? All good? Okay. Then let's go back to the question. See, now we know dissolve components. Towards the angle, we have the cos component. Away from the angle, sine component. Now, I'm going to dissolve this 60 towards the angle 30. So this is 60 cos 30. And using that same angle, I'm going to dissolve this to the opposite side, away from the angle. This is 60 sine 30. 60 sine 30. Right? So we know these values. Sine 30 is half. Therefore, 60 sine 30 is 30 newtons. No? And cos 30 is root 3 over 2. Therefore, this is 30 root 3 newtons. Okay, now by checking, listen, by checking the forces which are acting along the string, tell me in which direction 6 kg is going to accelerate, downwards the plane or upwards the plane. Check these values, check these forces and tell me. So you have to argue based on forces and tell me. What about 6 kg? Downwards the plane, no, upwards the plane, no. In terms of 4 kg, upwards the plane, no, downwards the plane. What's your thought? What's your thought? Okay, always listen. If you need to check about the directions of motion of the string, check forces acting along the string. Check forces acting along the string. Now, this force acts along the string. What's the value? 30 newtons. See, this force acts along the string. The value is 30 newtons. 60 sine 30, no? 30. This acts downwards along the string. And all tensions will cancel. And here, this force 40 acts along the string. This force 40 acts along the string. Right? 40 here along the string and 30 here along the string. From 30 and 40, 40 is the greater force. So therefore, that side is going to go downwards. So what happens is 4 kilograms go downwards, travel downwards with a simultaneously 6 kilograms accelerates upwards with same way because both of them are connected with the single string. Right? So this is how we identify the direction of motion. Very much similar to the previous pulley question I discussed. Only difference in this question is you have an inclined plane. Right? Even if you have an inclined plane, direction of motion is checked by checking the forces which are acting along the string. Right? Along the string 30 newtons here, along the string 40 newtons here. 40 means the battle. 40 means the battle. Right? Along the string, this side we have 40, that side 30. 40 means the battle. So that side goes down. Is it clear, students? Is it clear? Quickly tell me if it's clear or not. If not, I will quickly explain again. Quickly tell me. Zara, clear. Others? Respond, please respond. So at least put a reaction. Put a reaction at least, Shekina, okay. Okay. All right. Then application is same. Application is same. Apply F equals ma towards the direction of motion and get two equations. See, take this down and same thing now. Same thing now for 6 kg. Direction of motion is along the plane. So use F equals ma along the plane. Direction of motion is along the plane upwards. Use F equals ma along the plane upwards. Right? T is there to the same direction and this force 60 sine 30, that is 30 is opposite minus 30. Mass is 6. 6a, I will consider this as equation 1. Then 4 kg, its moving direction is downwards. So downwards apply F equals ma. Right? Downwards we have 40, upwards T, 40 minus T equals 4a. Consider this as equation 2. Right? Now again you have got two equations, two simultaneous equations. Simplify these two as simultaneous equations and find T and A. So does this not have internal reactions? No. Internal reactions are only if two objects are in contact. Right? Perpendicular reaction, there is a perpendicular reaction here. I didn't mark the perpendicular reaction because it is not tasked. Otherwise, here there is a perpendicular reaction. As we marked in the initial force diagrams, there's a perpendicular reaction, but I didn't mark because it is not needed for the calculation. That's why. Right? Otherwise, we can mark. take the respective motion, which contributes the motion, right? That's the only difference. Since we had an inclined plane, take the dissolved component, and from that dissolved component, 60 cos 30 is perpendicular to the direction, perpendicular with this direction. So therefore, it is neglected, and only 60 sin 30 came as 30 here, right? Okay, mention this point in red below the question. Mention this point in red below the question. Mention this point in red below the question. Check forces acting along string. Check forces acting along string. Check forces acting. Check forces acting along string. Check forces acting along string. Check forces acting along string to check direction of motion. 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 Next point, 60 cos 30 is neglected. Next point, 60 cos 30 is neglected. 60 cos 30. 60 cos 30 is neglected since it is perpendicular to direction of motion. Since it is perpendicular to direction of motion. Since it is perpendicular to direction of motion. Okay. So any questions about this? Any questions about this? Or is it all clear? Any questions about this? Or is it all clear? What do you say? Students, come on. Are you sleeping? Come on, respond. All clear, good. Others? Clear. දැන් බොරුවටත් ක්ලියර් කියනවා දැන් ක්ලාස් එක ඉවර කරන්න ඕනේ නේද? Okay. Right. Okay. All right. All right. Okay. So about next day, listen. About next day, it will be a full day that we are going to spend with applications of F equals MA. Right. Next day will be a full day. We are going to spend with applications of F equals MA. Right. So as I told you before, having this knowledge as a firm base from the things you learned today for next day is mandatory, because next day we are going to straight away start the applications, right? So we'll be getting the route before next week, right? So from the route we will be start doing all the applications, right? So again reminding, you have to join to the regular batch class on Friday, this Friday, from 3:30 to 6:30 this Friday onwards, right? So if you haven't completed your enrollment yet, you can complete. I saw few enrollments were coming even during this class also, right? So good. So likewise, you can finish your enrollments and get ready, right? Okay then. So if there's no any questions, we will wind up. So again, repeating, please go through the questions and the theory parts we discussed today and familiarize yourself, right? And be firm with the knowledge and come to the next class, right? If you have any more questions, you can contact me on WhatsApp if there's any more questions, right? So if there's no any other questions in the chat boxes, right, I'm going to wind up. We are going to wind up now. It's what's the time? 11:07, 11:10 almost, right? So I'm going to wind up. Tomorrow also I have to wake up in the morning because I have morning classes, right? So then we'll wind up. It seems no any questions. No questions, right? Okay, no questions. Then we'll wind up. Stay safe. Stay safe. And you are going to start your vacation Friday onwards, right? Utilize your vacation and study hard. Don't waste the time in your vacation. Right? Stay safe and study hard. See you all in the next class. Good night and goodbye. See you. Bye bye.